Welcome everybody online and here. Thank you for coming again for our lecture series on digital humanism. Sorry. I'm Sophie Lechler as always, and today we have two very exciting speakers again who will talk about their research that connects to the principles of digital humanism that interest us. And we're going to start with Professor Faribi Karimi, and she's going to talk about measuring inequality and fairness in complex networks. And whenever you're ready, we're looking forward to it. And then we're going to have a Q&A, and then we're going to go to our next speaker. Thank you.
Okay, great. And then I do this here. Okay, so thanks for being here. Good afternoon, everyone. I have a very interdisciplinary background. I come from network science and statistical physics, and the past 10 years I mainly worked with computer scientists and social scientists to address societal issues from the perspective of complex systems and complex networks. So to give you first a broader overview of the type of research we are interested in, let me tell you a little bit. So I'm interested in the question of group formation and the properties of the groups that define us and define how we bond with each other. And these tie formation mechanisms, the way we bond ties with each other in the macro level, creates these kind of social networks of people, larger scale structures that are not random, not coincident, and they have a specific structure, topological structure, and this structure is very important because it determines how information flow in the system, it determines norms and culture, it determines how we perceive others. Nowadays, this structure also fed into algorithms, into people recommender system, people ranking system. So whatever biases exist in the structure can trick into online systems and algorithm and can create a secondary effect, second order inequalities in a way in which it's difficult for us sometimes to comprehend. And in general, the interaction between machines and society and us are a dynamical process. It's something time-dependent, path-dependent, and dynamical. So it has this kind of properties of complex systems. So as somebody who comes from complex system perspective, I like to study socio-technical systems as complex adaptive system and use the techniques and methodology that we have developed in complex systems to also understand socio-technical systems and how inequality and biases are evolving in such socio-technical systems. So today I will tell you a little bit about how we are approaching inequalities in complex networks and how they manifest, these inequalities manifest themselves in algorithms and how we can tackle them. So let's start with some definitions that I use usually in my talk. By the way, is there a way I can forward the slides with a pointer? There's a point? Okay, it's okay. Yeah. If there's a pointer that I can use. Oh. Okay, perfect.
We found one. You have to plug it in.
Yeah, to plug it into what? To this one? Let's go. Okay. Oh, wow. Okay, magically works. Okay, thank you. Thank you. So, in my talk, I talk a lot about operationalizing the definition, the notion of minority. Minority in my computational models are numeric minorities. groups that are numerically smaller than other groups. For example, one of the examples of it could be women or people of color in STEM fields, in science and technology disciplines that usually they are numerically smaller than men, for example, or people of color compared to white. So most of the time, the minority groups also become marginalized group, meaning that it creates some disadvantage for them. And as a modeler, I'm interested in understanding what are those mathematical properties that creates a group, a marginalized group. And when we talk about network inequality, you might think of networking are always good. So what's the problem with that? Everybody has the autonomy and ability to create the networks that they wish to. But in reality, most of the time, we don't have that autonomy to decide where we are in a network. So if you are a physicist and live in 1920, and you want to talk to Victor Hess, a Nobel Prize winner in physics who lives in Graz, if you are from Austria or Vienna, your chances of knowing somebody who knows Victor and give you an introduction, have a coffee with him would be higher, right? But if you are somebody who is living in South America or East Asia, the possibility for you to find Victor or talk to him is much limited. And it's not because you're working less than other physicists, but it's just there are just certain physical and social boundaries that allows you or others to connect to important people. So we argue that it is always not in our hand to decide where we are in social networks, and I would also argue that nowadays algorithms can also contribute in this decision of where we are in social networks. So now, when we talk about structural marginalization, you might ask, why should I care about minorities? If they are a numerically smaller group in society, who cares? The point is that as we live in a complex society, this issue of disadvantages can affect all of us in one way or another. That's one point. And the other point is that basically we will not find innovative solutions if we ignore the presence of marginalized group, minority group, if we don't bring all the voices together. And this is very nicely presented in this book, Objectivity and Diversity, that in fact, if we want innovative solutions, we need to bring diverse groups together. Okay, so I focus on multiple forces that create marginalization and structural marginalization in social networks. One of these forces are social forces, self-selection biases, homophily, the tendency to interact with people that are similar to us, and so on and so forth. The other forces are time and space. The physical proximity and temporal proximity can also create structural barriers and structural marginality. Algorithmic forces nowadays can also add to this structural marginality, and also historical forces. There can be situations where some group in the past were marginalized, but the traces of those marginalization affect the structure of the society, even though the actors have changed and replaced by actors that do not have those bad intentions, but the structure still carries on those inequality and biases. So how do we look at social forces through computational models? So the first, one of the things that I started thinking about this problem was that when we look at a lot of ranking algorithms online, for example, this is LinkedIn, or if you look at Twitter or other ranking algorithms in Google Scholar, you see often ranking like this, where certain people are ranked based on some properties. Usually these properties of the rank is related to the structure, is related to who is popular and in relative to whom. So more popular and more prevalent people in the structure of the social networks are often presented in a higher positions in the rank. So in this example, if you look at a certain job, you would see that among top most important people, 1 out of 4 is a woman, for example. So I wanted to know how these the social aspects of how we connect with others affects our position in the rank. So it's even one of the important forces in society that bond us and blind us sometimes is called homophily, the tendency to interact with people that are similar to us. So this is a friendship at high school in the United States. You see clearly the separation of groups between colors that is actually related to racial differences. So black and white students are separated in terms of their friendship. And this is also political communication between Republicans and Democrats in political blogosphere. So very innocent social force called homophily, the tendency of interacting with people that are similar to us, in the macro level, create these large-scale segregated communities where like-minded people are more likely to be connected. So what we decided to do, we decided to operationalize the notion of homophily in social networks, to generate social networks that are operating based on 2 fundamental social mechanisms called preferential attachment, or rich gets richer effect, and homophily, the tendency to interact with some other others. So what we did is we built a very simple social network model that the probability of nodes arriving to the system to connect to others is related to popularity of existing nodes and homophily, the relationship between the colors. So these are very simple items in the graph. Graph consists of nodes and edges, and with this simple kind of model with 2 parameters of preferential attachment and homophily, you can generate a variety of social networks. If you have questions, you can also ask the audience. You can write away, or we collect questions afterward. Okay, so what is nice now is that we can now look at a lot of hypothetical scenarios of social networks, tuning the value of homophily while fixing the number of minority and majority groups, and see what happens to their property. Okay, so here I have the fixed number of minority and majorities. Minorities are orange, majorities are blue. Minorities are 20% of the population. And the only thing that is different in these scenarios is the value of homophily. When homophily is high, we have a tendency of groups to connect to other groups that are similar to them in terms of color. When homophily is low, we have actually heterophily, meaning that people of a different color attract each other. So what is interesting here is that just because of the differences in the intensity of interacting with similar colored nodes, you see emerging property of degree distribution, meaning that the probability of finding popular people in the tail of the distribution become a function of that homophily. To see that more clearly, if now we rank people based on their position in the social network, and we assume that minorities are 20% of the population, we might say that they need to appear in all the ranks 20% of the time. So this is top 10%, top 20%, top 30%. Remember, we are now simulating what happens to these ranking algorithms that we have, like LinkedIn and Google Scholar, okay? So now what happens when we have high homophily of 0.8, is that minority group do not appear in the top rank compared to what we expect from their size, which was 20%. So what it means is that even though our networks, our social networks are innocent, the actors are the same. The only thing that are different in these scenarios are simply the value of homophily. It has this emerging effect that minorities become underrepresented in the rank just because of the way they connected with other minorities. And this only happens for minorities, and this is just because of their size. So what it means is that groups of various sizes and the probability of interaction with other people creates these mathematical boundaries in which people can become more visible or less visible in the ranking systems. So this gives us a very nice kind of computational tractable tools that would allow us to understand what happens in these black box kind of methods. Many times we see, okay, minorities are not visible in the top rank, but why? Why they are not visible? And this with these computational models, we have actually parameters that we can look at and we can trace back why these things could potentially happen. Another effect we see with the increasing level of homophily is the formation of core periphery structure, or rich club. I don't want to go to too much detail, but rich club is a concept that is very close to the concept of, maybe you have heard boys club or something like that, when you have a club of people in an organization that are very influential, they are very well connected, they make all the decisions. Okay, those in network theory they are called rich club. So very well connected people and well connected among each other. And what is interesting is that as homophily increases, you see the formation of rich club that are usually the majority in this scenario, which means that basically this homophily not only can marginalize the minority group, put them in the periphery, but also creating a situation where they cannot be possibly in part of the rich club. Okay, so this is the social force of homophily that can create a structural marginality. Now, what is the effect of time and space? I think this is very interesting, and sometimes we forget about this effect. So when we meet in a conference like this, when we meet in a coffee break, we are making a decision that I spend this time and space with you now. And that means that I have excluded the time and space to meet other people. And these decisions, of course, we live in a limited time and space, so we make decisions of whom we interact and whom we exclude to interact in every time point. And I think it's very interesting to study how this time and space constraint affects how people interact with others. We are doing a similar thing in the city of Vienna. We are looking at where immigrants reside in Vienna and what it means in terms of the homophily, the tendency of immigrants of certain origin to reside in certain parts of Vienna together. And we find similar results, meaning that we see homophily among residents based on their immigration background. So I'm gonna skip this. So the way we approach the question of time and space is that we have now people moving around in a physical space, and they interact with others given the physical proximity. So this person is likely to interact with these two other persons based on their attractivity, which is a parameter that ranges from 0 and 1, and physical proximity, meaning that this person decides to interact only with these two people, not with other people, because they are far away from this person. And what we see in this type of model is a very similar scenario that we saw before. So we have now 3 different social networks of minority and majority. In one scenario, we have a low homophily and high heterophily, meaning that yellow likes blue and blue likes red. And we have a scenario of high homophily when blue likes blue and yellow likes yellow. And what you see in terms of the degree distribution, degree is the kind of a proxy for social capital, how many connections I have, or how many connections I can potentially create. What you see here is that when you have high homophily, majority's degree takes over the minority's degree. They have, on average, higher degree than minority, which means that potentially they can have higher social capital and connectivity than minority group. And vice versa. You can have this situation here where minorities actually are more popular because of heterophily, and because there are more majority than minority, they become this super rich hub in the system. This is one of those scenarios that heterophily actually doesn't translate to marginalization for minorities. Minorities are actually the rich people in the social network. You can think of them as celebrities or politicians. These are minority group in the population, but they are not marginalized group. They're actually very well connected to themselves, and population like to be connected to them. And in this scenario, you see that the minorities' average degree exceed the majority's average degree, meaning that they have more potential to attract social connections. So what you see from these computational models is that basically our ability to create social connections with others, even if we are all have similar properties, actually create some mathematical constraints in which can make us more visible or less visible, and can affect our ability to basically receive information or spread information to others. I hope I am understandable. Okay. So in recent years, we have become even more interested on the question of time and space. For example, the question of cities. How do we design cities that makes integration easier, that creates a place for people to hang out, especially people of different backgrounds, people of different socioeconomic status, and so on. And in fact, there are a lot of recent papers coming out in Nature Communication and so on that shows that actually the design of the city is very important in terms of creating places where people of low socioeconomic status can meet people with high socioeconomic status and so on. So in that direction, in one of the recent research we have been doing with scientists from University of Chicago, is to look at many states in the United States and study the racial segregation in different cities in the United States based on available census data. Another available data that we have in our disposal is this association test, implicit bias association test, meaning that you ask people to associate certain characteristics such as joy, excitement, I don't know, with this good, bad, or black and white. And it turned out, and these are very fast-paced experiments, you can actually do it online. Have you ever done this implicit association test? Yeah? It's interesting. I have also done it myself Because if you have enough time to think about that, okay, good and bad is not related to black and white, you will do it correctly. But if you are in the time pressure, it touches upon these implicit biases, meaning that you don't have enough time to think about it. You just have to quickly decide, okay, good is white and bad is black, or something like that. And it turns out it's a very good test in figuring out people's implicit biases. So we look at the interplay between the implicit biases of people and also the racial segregation in the United States. And what we found is that more diverse a city is, and more, not only diverse, but also more disaggregated the city is, peoples in general have lower implicit biases towards other racial groups. Okay, now let's talk about algorithms, which relates very strongly to the Digital Humanism award that we got 3 years ago, and we are still working on this project together. And the person who is behind, leading all the work is Lisette Espin-Noboa, who is our senior postdoc in our lab. So if you think about a lot of online social networks, such as Twitter or X or Google Scholar or web hyperlinks, we are dealing with directed social networks. Who follows whom? Who cites whom? Which link basically refer you to other links. So we are dealing with a directed social network. Now, directionality has interesting effects because you can generate social networks. For example, in this scenario, blue likes red, red also likes red. In other scenario, you can create situation where blue likes blue and red also likes blue. So you can create asymmetrical interactions. And asymmetry, I think it's very interesting and important concept in social network analysis, that our tendencies towards others is always not always reciprocal and symmetric. And this relates to social status. So with this, taking into consideration the directionality in social interactions, we are now modeling social networks that consist of minority and majority group, but also asymmetric interactions. And we can control this asymmetry by these parameters, 2 parameters for homophily. One parameter that determines the strength of interaction between majority to majority, capital M, and strength of interaction between minority to minority, non-capital M. And with that, we can create many different scenarios of symmetric or asymmetric social networks. Then what we do is that after we generate these networks, we rank people again based on their social position in the graph. It can be page rank, for example. Page rank is basically the algorithm behind Google. You can rank them also based on social recommender system that, for example, Twitter has or X has, that is called whom to follow. And then you rank people, and then you look at where they are, what is their social position in the social network. So this is basically the way we do it. We rank people, blue and orange. We compute the page rank, and then we calculate mean error rate and Gini coefficient to determine whether minorities and majorities are represented in ranks based on what we expect from their size, given that all else is equal. So to see this effect of asymmetry here, we are looking at minorities homophily that ranges from 0 to 1. We are also looking at majority homophily that ranges from 0 to 1. And here, minorities are 20% of the population. So what you see here is that regardless of minorities' strategy in regards to be very homophilic, or very heterophilic, since there are only 20% of the population, as long as majority is slightly homophilic, minorities are always underrepresented. Red means underrepresentation in terms of the ranking equality. Minorities become underrepresented in this scenario. And this is basically suggests that in scenarios that they are numerically small, they have limited ability to determine their visibility and their position in the rank in social networks. Okay. Now the effect of algorithms is actually more important if we think of the feedback loops. Because what happens in reality is that we have a social network, then we have a ranking algorithm or people recommender system, and this recommendation affects how people are ranked and affect our decision of whom to connect. So the idea of whom to connect or people recommender is, of course, for you to click on that person and connect to that person, right? So what is happening here is that through this feedback loop, our social network is fundamentally changing as in relation to this mediator that affecting our observation. So the world we observe is now going through a mediator called algorithm that affects whom we look at, whom we connect to. So what happens is that in this paper in 2022, we found out that if we run this feedback loop for multiple iterations, and then we calculate the properties of the social graph after this multiple iteration, we see that the social graph become more cohesive over time, meaning more segregated also. Minorities can become more connected to minorities, and majorities can become more connected to majorities, creating this filter bubble as a result. Another result that we recently found is that, let's say we are looking at in which ranking position minorities are 30% of the population. So in a neutral case, minority should be 30% of the population in the ranking position of 30, okay? But if we have a feedback loop, it starts going up, meaning that you need to go to the 70% of the rank to see 30% of the minorities. So they become more and more peripheral in the social graph. They become less and less visible through this feedback loop. Remember that the whole mechanism remained the same. The only thing that is now changing here is the feedback loop. So more we wait for this algorithm to happen in society, more our social networks become fragmented. And I think this is a good example to show that we need to use these computational models also to forecast the risks that can happen to AI systems and have more proactive action in terms of avoiding and preventing scenarios that we would not like to see in society. And one of the things we are dealing with at the moment is filter bubble and echo chambers that is actually happening as a result of these recommender systems. So to concretely give you an example, we looked at the perception of people depending on their position in the social network. So if you ask the pink person here to estimate the size of the pink population, she would overestimate the size of the pink population because of her worldview, right? She lives in this homophilic network. If you ask the green person to estimate the size of the green population, he would also overestimate the size of the green population because he lives in this part of the network. So we did some experiment with real survey data, but also with simulations, and we look at the homophily as a result of and its interaction with perception bias. So the dashed line means no bias, and the values beyond 1 means overestimation of the minority group. The values below 1 means underestimation of the minority group. So for majorities who live in these homophilic networks, they underestimate the size of the minority group. While for those majorities who live in the heterophilic networks, they tend to overestimate the size of the minority group. And what we found very interesting is that if people would talk to their neighbors and average their own estimate with the estimate of their neighbors, they can actually correct for their perception bias, but only if they live in these heterogeneous networks. If they live in networks where their neighbors think similar to them, correcting your perception with the perception of your neighbors doesn't help you to correct for your perception bias. But if you have neighbors that are different from you, their perception is different from you, and then you average their perception with your perception, then you can actually correct your perception better, which is very interesting. It suggests that basically living in these bubbles and echo chambers not only affects our perception, but creates this illusion of normative kind of rules, meaning that we think that whatever we think is what society thinks, because other people around us also think the same way. So we have this conformity. How much time I have? We need to finish. Okay. Okay, then I will go to the question of fairness. So now that we have some inequalities manifested in our complex networks, how should we approach correcting them or approaching fairness? And this is not an easy question, but this is the task of me and my colleagues for the next 5 years through the ERC grant that we recently got. So we need to ask ourselves, how do we define fairness in social networks? What are relational fairness? For whom are we correcting this fairness? So we can talk about individual fairness, we can talk about equality of opportunities and distributive justice, we can talk about group fairness, and we can talk about network fairness that we want to do. We can look at correcting algorithms, we can think of manipulating the social networks, but we need to always consider who are the stakeholders, what is our moral goal, is it justice, autonomy, what is it that we are going after? So these are all open questions that we're going to be busy doing for the next 5 years, and I would be happy to hear more from you. I don't make this, so I would say thank you. Yes, yes.
Okay, we have time for questions now for Haribe on, maybe also on her ESC project. Great. Who wants to start the question? So maybe while you're thinking, I can start. It's always, I take it. So I'm a social scientist, so please excuse me if I ask a stupid question, but actually I'm basing my question on an earlier lecture we heard from Julia Neithardt from the TU. And she talked about recommender systems from her point of view, and I know that's not the same type of research, right? But I'm trying to square a little bit some of the kind of findings. So her point was that when they look at recommender systems, be it music recommender system or any type of news recommender systems, there is also a hint that, for example, recommender systems compared to human recommendation cause a larger diversity in what is recommended to people, right? So basically actually cause a more healthy access to information or music or whatever it is because of the way they are designed, right? So there's these studies that compare like what if journalists recommended news to people or if an algorithm recommended algorithm actually caused more diversity and more inclusion and the journalists are more biased simply because a journalist doesn't know all of the articles that have been written on a topic. So I was wondering also in your type of research, when we think about people recommendations, how do you kind of like make more the conceptual comparison between algorithmic recommendation and human recommendation? In a sense, if I ask you now, maybe can you please point out the 5 greatest people in the University of Vienna? You make a recommendation based on your bias, right? So is this just a similar bias that was there in humans before, now it's in the algorithm, so it's basically just the same thing in a larger thing? Or can the algorithms also do, take away some of the bias that we as humans inherently have? I don't know if that question made sense.
That's a super interesting question. Yeah. Thank you for asking. I don't have a good answer.
I'm sure you do have an answer. There's not only one answer, I'm assuming.
In fact, a lot of rationale behind the people recommender system is actually following what humans would do and what humans would accept. So they are based on the natural biases we have. And by the way, these biases that we have are deeply rooted in evolution. So we cannot really forget about it, and we need to take those into consideration. So yes, they are using the same rationale, but in a big scale. So in human level, we have our own biases, but we are heterogeneous in our biases. I have certain bias, you have certain bias, this person has. And it turned out this independency and heterogeneity is actually good. It creates diversity, serendipity. But now what is happening is that all of this now will be aggregated in one piece of information to one AI agent. And that doesn't have this serendipity, doesn't have this heterogeneity. It has everything, all the information. And I think that is the issue, because we are evolutionarily not designed to have complete information about everything. We need local information to navigate our social world, and I think that's the issue.
So I'm just having a conversation with Faribi, but you have a question, I'm assuming. You were just like, go ahead, ask more. But do you have a question as well? No, you go ahead. I'll come back to mine. Hang on one second. For the online viewers, we need to...
It's completely jump to... Wait. No, I got so hung up to saying you should continue. And the one thing, the EIT, it's kind of controversial. So what was exactly, how was it applied and how was it used? Because like this very fast-paced response measuring is very unreliable in a lot of different environments. And I completely didn't get the point how it was applied and what actually was like the message from it.
The implicit association test. Yeah. So we look at the implicit association test of different racial groups in different states, in the US. So basically, we correlated those implicit association tests of people based on their racial background with the mixing of their census, with the census data that explains the racial mixing in different districts in that city. Because the IAT test is also it tells us in which part of which district that test was done. So we can see we see a positive correlation between people who live in a more mixed districts have lower implicit biases towards other.
Interesting, because like in psychology, we always criticize the shit out of this thing.
Okay, I'm sure that
it's still always really interesting because it's catching something, or it's trying to catch something very interesting, but it's so hard to actually use and implement it well. My other question is more about how you, like the thing you sketched around fairness, like how you define it, who is important and when, because like, I would like more information on that, or your point. So like how fairness would look like.
Yeah, how fairness would look like. I think to relate that question to some of the earlier work I showed with regards to the distribution, for example, we see clearly that the distribution of where people are in the social network as a proxy of their group size and, let's say, social mixing. So more homophilic and minority a group is, less likely that they happen in part of the distribution that they will be advantaged. We have this skewed distribution. So this I am now hypothesizing, I don't have answers to this, but I think we can take ideas from distributive justice by John Rawls and think of, can we think of bringing the least advantaged people in the social network a bit towards the core in a way that doesn't compromise other people, and they still benefit from the social capital that is embedded in their social network. So that could be one way of operationalizing the question of fairness in social networks. In algorithms, we can do this. For example, I showed you the ranking, for example, PageRank, and scientists have defined like fair PageRank. What if the PageRank is manipulated in a way that minorities appear higher in the top ranks? But I would like to approach that more systematically, meaning that, okay, if we make this fair, fair for whom, based on what moral values? So I think these are more deeper questions that requires more investigation.
Thank you.
Thank you. Time for one more question, if you have one more. Yes.
You just mentioned moral guidance, and you probably heard about the Matthew effect, as in Bible. So that what you mentioned, rich get richer and poor get poorer. So it's a Matthew effect. Described it already in the Bible. So if we consider from this perspective, is it already embedded, the fairness, in our, let's say, human society? So probably we should not change it.
How exactly the fairness embedded? I mean, rich gets richer, right? But poor gets poorer. It's not fair, no?
Well, but it's embedded. Let's say it's already described in the Bible. So if we change this, we are going against the Bible.
Against the Bible?
Bible, like the famous Matthew effect.
So is bias, if you say bias is human, why do we need to go against bias? I think that's the point, right? So is this such a fundamental thing? No, not your point, but that's a question, right? So yeah. Maybe it's also a point, what is fairness? I think that's the question then, right?
I think I am not in that position to answer the question. This is, of course, a question that you can also ask John Rawls and all these moral philosophers that argue that we as human society are better than animal kingdom in terms of also making the next generation better off. I'm not in that position. But what I can say is that beyond evolution, beyond this competition for limited resources, these are the natural processes that we go through, similar to other social animals. Algorithms are mediating. We have now new agents that are not human and also helping or mediating some of these effects. And I would argue that it's our responsibility, maybe perhaps moral responsibility, to understand how are they mediating in our lifetime. Should we allow them to act as normal agents in our life, or should we look at what properties they have? How are they perhaps manipulating or helping our society to better off, at least for the next generation?
Thank you. Thank you so much for your presentation. Excellent. Thank you so much. Thank you. All right, we go to our next presenter. So, our Our next presenter is Sabine Kusegis from the TU Wien, and she's going to talk about man-machine competition or symbiosis. Q.
Now it works? So, good night, everyone. Thanks for having me here. I will connect a little bit to your talk later on when I talk about diversity and wisdom of the crowd and the use of AI. I'm a labor scientist from TU Wien, and I do research in the intersection between organization, human beings, technology, and I'm particularly interested also in the human-machine interface. And I was involved in various policy advising bodies, like, for instance, the AI high-level expert group on artificial intelligence, where we developed ethics guidelines. So this is also, my work is also very much informed by policy, ethical guidelines reasoning. What you see here is a watercolor painting. And the question is, right, so I want to invite you to switch our perspectives, because the question is, yes, if you ask an AI, give me a watercolor painting of a woman, you will probably get a very nice picture. And this is what we tend to do when we compare, when we start comparing human performance with AI performance, we look at the results. But we miss out the whole process of painting, right? In this case, of producing something. And so the question is, yes, maybe an AI algorithm may play better chess, but it has no fun in playing, right? While we humans enjoy playing chess, right? And we play for the joy, right? Or we paint acrylic pictures because we want to master painting, or we want to get in dialogue with ourselves. We want to say something and get in dialogue with someone else who is watching at our pictures or something, right? So the question that we have to ask is, what is happening to us while we're doing something? And what is, so we have to focus on the process. And this is particularly necessary if we talk about using AI in the work environment. So I have not been here, so I don't know how much you know about AI technologies, about its development, and about anthropomorphism, but I will talk a little bit about it. But then I will jump into the two basic visions that, or narratives we find out about AI in work, and then I will talk about the implications for the design. So when I talk about AI, I think this is important to understand. We talk about very, very different things. And the first time, you know, something what AI could be turned out in a paper by Alan Turing, who wrote about mind and the imitation game. And he wrote about this idea, what happens if we create machines that work similar to our brains? And that was basically the first time where we tried to imitate human beings, at least in a thought experiment. And the first time we talked about artificial intelligence was this famous Dartmouth conference, where some researchers thought they're going to ask for a couple of $1,000 and then they're going to develop AI within 2 months during a summer retreat, which we know did not happen. But this was, so to say, the birth of the idea that we could build machines that mimic or imitate or resemble human beings and their intelligence. And then what you see here is that we had a lot of steps towards, introducing robots, introducing self-aware robots, introducing chatbots. Like the first chatbot was from Weizenbaum Eliza, who was a very simple program mimicking a therapeutic conversational agent and so forth. And what you also see here is that we always had very high expectations in AI technology, but then we were frustrated because it didn't work out. And it didn't work out as we expected, and we finally are now here somewhere in 2022. I stopped, with ChatGPT being introduced as the first large language model generative AI tool, and then, and again, it seems that we had a strong hype about generative AI, but it seems that expectations are dampened already at the moment, realizing, well, intelligence is something different. Nevertheless, there are huge expectations on how to use them in this technology in the context of work. And so I would like to very briefly introduce the secret sorcery, what people might think AI would be. And basically, it consists of algorithms that are logical sequences, that. And the important thing is that they always consist of a formalization of a problem and a goal. And we talk about algorithmic systems, and that's the important thing, whenever human judgment is completely or partially replaced by these algorithms, right? Then we talk about algorithmic systems, and the advances for in AI technology are possible because we developed neural nets and deep learning technologies, and we developed the transformer technology that is able to process natural language in a very efficient way. Now, that was just to have a common starting point of the endeavor that we have. And the first thing I want to stress is that already Searle in 1980 in his paper Minds, Brains, and Programs was proposing the thought experiment, the Chinese room, where he demonstrated that basically the ability to process science, even be it so complex and efficient as a neural networks, etc., that it remains syntax, right? It remains simply simulating, predicting, estimating, calculating, but there is no semantics in there, so that while human beings would work on a very different mode. We are sense makers, we do judge, we do understand, we do evaluate things, and that's a very different mode of processing information. So that's basically the fundamental difference, and that brings a lot of issues with regards to human-machine collaboration, because we need to translate our very different way of thinking and reasoning and judging mode of operandi, we need to kind of combine them when we want to collaborate. So I was instructed also to say something about anthropomorphism, and I try to get this thing running, but I don't know. I should be able to start it here, but it doesn't work. Yeah. I just explain it. This is an experiment by Heide and Simmel done in 1944, and what you see here, usually if you start this little video, you would see that the triangle and a dot and whatever is moving around in here and on the screen. And they ran this little film and asked people what they see here and what they describe. And then, you know, they would describe, well, they would not say there is a triangle moving from the left top to the right bottom and so forth, but they would say, well, there is something going on. They play hide and seek, and this is a very aggressive dot, and he's trying to hurt someone and things like that. So what we do is we ascribe human characteristics to moving objects. And that is anthropomorphism. So we tend to ascribe human characteristics to things. We talk to our cars and computers and to the coffee machine, and we think that they are mean to us if they don't work, and so forth. So that is a very normal thing. And in the design of AI technology and computers, we tend to use this mechanism because it increases technology acceptance. So anthropomorphism increases, and at least to a certain extent, our technology acceptance. Why does it do that? It eases interaction. So if you can program a computer through natural language, which is basically prompting in ChatGPT, right? Then technology acceptance increases because it simply becomes easier. If you had to write the same thing in Python, you would have high hurdles to enter the technology, and the technology acceptance would be much lesser because the ease of use is not there. So natural language, etc., and anthropomorphic designs of robots increase the technology acceptance. What is the downside of it? You also introduce expectations that the technology would behave as if they would understand, right? So, you know, you would, if you ask a prompt or put a prompt to ChatGPT and the prompt and so the system answers, you would start thinking that the technology is understanding what it is saying. You are not aware that it is in that moment, that it is merely probabilities that it is coming, that are basically presented to you in forms of words. And that's the problem. That's one of the problems. So anthropomorphism eases the interaction with machines. It facilitates technology acceptance, but it triggers perhaps very false expectations, for instance, about the intelligence of the tool. And of course, with, you know, making machines similar to humans, we introduce all sorts of stereotypes and biases into the technology. That's an issue. So it is used, anthropomorphism as a mechanism is used in the design of AI technology. However, we have to be careful. And I would like to ask a very fundamental question here then. whether or not, you know, the two fundamental paradigms of designing machines, how successful they are. So basically, I'm asking the question, if you go out and look at the discussions you find in the public discourse about AI technology, you find basically two different visions or versions of machines or machine intelligence. The one is, and that is the one that used this anthropomorphic idea. You simply copy the human, but make it better, right? This idea goes back to Alan Turing, and it's the argument is if we understand how our brain works, how we are thinking, we can imitate that. And the idea is that we develop machines that are better, more reliable, and less erroneous than human beings, right? Machines do not have the needs to sleep. They are not sick. They can work 7 days, 24 hours. And they are not, if they are developed well, they're better than human beings. They can, you know, process so much more information, et cetera, et cetera. If we follow this idea, at the end of the day, we will end up with the Homo obsoletus, which is a term coined by Yuval Noah Harari, and also taken up by Anders Inset and others. So it's the idea that the machines will work for us, and we don't need to work anymore because we have these perfect machines. Another perspective is this, that we could create machines that are symbiotic to us, right? This idea goes back to Norbert Wiener and Licklider. And here the fundamental approach is completely different, right? The approach is that we asked, what do we need the machines for? What should they do, right? Where do we need support? And we create exactly those machines that are needed and wanted for us, right? And we let them do the work that is dangerous, that is difficult, that is boring, that we can't do anyway. And they support and enhance us in our capabilities. And here, of course, the idea is that we stay in the loop, and that we are the autonomous human beings that decide what is going on and who keep the full agency. Now, let's look at empirical evidence in which direction we walk and we go, right? So the most recent study by McKinsey Global predicts that in 2030, so in 5 years, 30% of today's working hours could be already automated. And that is due and caused by particularly not only AI tools, but particularly there is another boost through generative AI. And this is irrespective in which industry you look, right? It is STEM professionals will face automation. Programming with ChatGPT is so easy. You don't need to know Python anymore, right? You just need to, yeah. I just talked to a colleague today, and he was demonstrating how easy it is to let little programs, standard programs be performed through ChatGPT. So whatever you look here, there's no industry which is not affected. How does it work? There is a wonderful paper by Brynjolfsson and colleagues of MIT, Generative AI at Work. In this paper, they demonstrate, this is a field experiment with a company with 5,000 agents working in a customer service, right? So it's not a prediction anymore. This is a field experiment. And they use a ChatGPT-based service tool and ran experiments with a treatment group and a control group. So what you see here, and it works like, you know, there is a customer complaining in this case that the website is down and it doesn't work and that he's losing money and they should immediately fix this problem he has on the website, right? And ChatGPT produces alternative answers, and then the agent decides which answer to choose, adapts it, and to the customer. And what you see here is the blue line is agents never treated on a tenure of 10 months. All start out with approximately 1.5 to 2 customer requests treated in 1 hour, right? So almost 2 in 1 hour. The blue ones never treated, they never get the system. They increase their to 2.5 their number of customer requests answered. The green ones were not treated for the first 6 months. They developed similar than the blue ones and then increase their efficiency. The red ones were treated from the beginning, so they had this AI system from the beginning. And they increased their performance within 6 months to 3.5, so almost double their performance. So AI is significantly increasing performance, generative AI. This is empirical basis, facts from a large study. What they also did is they looked who benefited most from the system, right? And this is what you see here. You see here that the agent skill at the AI deployment in the first graph on the horizontal axis and the resolutions of customer requests per hour. And you see the higher the skill of the agent, the less they benefit from the technology. So if you are a good skilled worker, you don't benefit at all, right? If you're not good, if you're not skilled, you benefit a lot. And the same is true for people with tenure, which is basically experience. The more experience people have, the less they benefit from the technology, which at the end of the day means in order to realize the economies of scale and scope and efficiency gains, so companies will either replace workers completely or replace skilled and experienced workers who are expensive with less experienced and less skilled workers being much cheaper, and equip them with AI tools. That is what is going to happen. Otherwise, you can't realize the economies of scale and scope, right? This is what you want to realize through AI technology. This is what we are going to see. Now, what happens if we do that? David Otter has done a study where he looked at what you see here, where he looked at the change in weekly wages in the United States. And I think you get the same results in Europe if you look at that. From 1963 to 2017. And what you can observe here is, so it's for men and women, 2 graphs, but what you can observe here is 3 phases. The first phase is between 1963 and 72, which is basically economic growth. And you can see that every education level increased during this time, right? So everyone benefited from economic growth. Then there is the stagnation phase, 72 to 79, the oil crisis and world economic crisis, every wage, no matter which education level you have, stagnated. And then from the 80s on, we see digitalization. And what we see there is that only well-educated people benefit from economic growth. All others stagnate or see wage losses. And now, if you think what is going to happen through generative AI and the effects that we have seen before, that people are basically expropriated from their knowledge and skills because they can't bring it on the labor market anymore, you will see that particularly those people in the medium level will not benefit or will see a decrease in their wages. And only a few people will benefit from AI technology if we develop it in the way where we automate tasks as we do currently. Now the question is human-machine symbiosis, is this the resolution? So we do not automate, so we do not build AI systems that automate tasks and replace human beings, but rather have, AI in the loop, and where we have the human agency resting. So agency resting with the human. So here we would, as Licklider said, we would have enhancement through the AI, we would have human oversight and control, we have accountability rests with the human, and the human takes over when something goes odd or is out of the loop. This is basically what we suggest in the ethics guidelines of the European Commission, and this is basically what the new regulation requires. The human in the loop, the final decision rests with the human. However, this design also comes with problems, right? Because we have things like, and this is a reference to the computer sketch, The Computer Says No, from Little Britain. I think you probably have seen it. Just a quick sketch of it. A mother goes to the hospital and wants to register her daughter for a Manteloperation, whatever this is in English, tonsils surgery. And this nice lady argues after typing in the name that it is for a hip operation. And then, the mother says, well, that's not reasonable, and tries to convince. And this nice lady always says, the computer says no. And what we mean is that people tend to trust computers more than, for instance, their own feelings or their own knowledge. We call that automation bias, and it happens quite a lot. We know that from previous automation rounds. And so there is a very, very, very recent study published just in November now from MIT, where they did a meta-analysis of 106 experiments, quantitative, taking the effect sizes into account of overall 340 effect sizes, where they tested in different experiments with different tools whether this human-machine AI, so human-AI synergy, really exists, right? And they figured out in the majority of experiments, human-machine combination, so a collaboration of AI and machine, performed worse than either the better AI tool or the better human. So just looking at that, it simply says, well, you know, even if we have a very good machine, it is very likely that it is not the best idea to put human and machine together, because the human-machine interface doesn't, or it needs a sophisticated design in order to enhance really the performance of a human. They also tested the comparison of human-AI symbiosis with human performance only, and figured out if you compare AI leveraged humans, then this works better in 85% of the cases. However, these results can only be achieved, so human-AI combination, if decision makers, and that's important now, if decision makers have a good judgment and a high level of confidence in their own skills. Otherwise, the automation bias would fall into the problem again, right? Because then people would again trust the machine much more, even if they have better information. And the most significant performance increases can be achieved for content creation tasks and not for decision-making tasks, right? Because in content creation tasks, the AI can perform routine parts of the task more efficiently. So the problem is, and that's what I show here in this graph, is the problem is if you combine human and machine in a collaboration, empirical evidence shows that the agency moves towards the machine, and instead of having an AI-supported worker, we rather have this picture that, you know, the worker or the human mediates the relationship between the AI machine and the system. And there are a lot of issues that we have. It's not only the automation bias, but it's complacency. So people tend to lose focus and concentration when they are just controlling and supervising machines. We have the Dunning-Kruger effect, which would be kind of the opposite of the automation effect, that you would overestimate your own know-how and do not rely enough on machines. We see already that it changes professional identity and self-efficacy of people. So people tend to lose their self-efficacy if they collaborate with machines. We have de-skilling effects. So people lose competences and skills or are not able to gain them from the outset if they collaborate with machines. Right, so we have this issue that we don't get the performance that we want. And another problem is, and that is now referring to what we heard in the previous talk, is Fügner and colleagues, what they did is they thought, okay, what happens if we use AI technology to support our problem solving and decisions? And when we compare this, not only when we as an individual are supported, but when we compare this, when we have groups of people, up to 100 people, which would be then wisdom of the crowd, right? Because we have the idea that if you use, and that's the point, a lot of diverse people, right? You have diverse perspectives on problem solving, and then the problem solution gets better. And these experiments, what you see here is, on the one hand, the T1 line, so the lightest line here, this is a group of people who had no AI support at all. And yet what you see here is the crowd size. So one person, a group of 2, a group of 3, a group of 5, etc., until a group of 100. And then you have another group, a treatment group, who had AI support, and the third group had AI support with a suggestion and a certainty information about the failure of the system. And the interesting and not surprising thing, it supports completely the experiments before. If you give an individual AI support, then these individuals outperform other individuals without AI support. If you give the same task to groups of 2 or 3, this is still the same. So groups of 2 until 4 or 5 are better if they are supported with AI. But if you look at groups of 100, right? So you use the wisdom of the crowd, then you can see that the group without AI support, so never used AI support, outperforms all other groups. And that is because you would lose heterogeneity and diversity through AI support. Just an example, if I give my students, ask them to write a thought paper about a scientific text, right? Then I received, let's say I have 50 students in my group, I received 48, let's say, different thought papers, right? People reading a text, writing a thought paper about it. If I do the same today, and they ask ChatGPT to give me a summary and a thought paper, I receive 40 different, or let's say 10 different papers, and the rest is the same. So the point is, if we discuss then in class, I get only a few perspectives, and that is what is happening through the use of AI systems. We tend to converge to the same opinions, lose diversity, and lose our capacity to resolve problems. And that is a problem that creates commons dilemma. Because if you look at this is another very interesting study. With the introduction of ChatGPT in the countries that had access to ChatGPT, the access to Stack Overflow, which is a website where people share their knowledge about, I'm speeding up, just, yeah. Yeah. So they, what I wanted to say is people are not contributing anymore to share their knowledge on websites like this, right? Which again increases our capacity of problem solving, right? So basically what I wanted to say is we need to design the systems in a way that allow to make a good man-machine symbiosis, right? And this requires effort. We cannot simply just introduce AI systems and that's it, right? No worries. Yeah.
Thank you so much. This was excellent. Now we have time for a question, unfortunately only. There's one. I have one, of course, but I'm asking the audience if you have one before we close for today. Yes, yeah. This is your moment. Hang on a sec, I'm running to you. Okay, coming.
Thank you. I have a question following basically your presentation and the previous presentation, Professor. So at the end, AI would kind of take over the jobs or work. So majority of tasks performed by humans will be handed over to artificial intelligence and robots. And this would create so-called technological unemployment. So basically that the people, let's say 50% or 47% of the people would not be able to find their jobs anymore. And previously there was such a, let's say, notion of leisure class, but this was very small number of people, aristocrats and so on. Is it possible to, in your opinion, to extend this leisure class to the, let's say, 50% of our human beings? What do you think?
I didn't get acoustically the...
So is there can we have a new leisure class of unemployed people because of technology, so to say? So what are these people going to do, maybe? Or, yeah? Can we extend the leisure class to the people who will be replaced by AI? Are you asking for yourself? Yes? For yes. Yeah. What's happening to the people? Maybe.
Yeah. First of all, I'm not so convinced that it will be leisure that we have. Because what companies tend to automate is what is economically feasible to automate and leave the rest over to the human beings. And to be very provocative, we will remain the hands and the legs because we have a good dexterity and that's not so complex, but we will lose it, we will have our brains. You know, Henry Ford once said, I ordered a pair of hands, but unfortunately they came with a brain. And now I think we are exactly there. With generative AI, we will have AI tools do the brain work, and we remain being the hands and the legs. So I don't think that we're not working, but I think we're not paid for working anymore, and we're not paid for thinking in the extreme, because we do that machines and some high-level experts. That is one of the problems. We see that already, for instance, in automation think about flying an aircraft. We have issues of finding pilots because they say it's not fun flying anymore. Because I'm sitting there and I'm just, there's so much automation in there, I'm not able to do anything. I'm just, controlling systems and, doing basically what is left over and can't be done by machines. And I'm just pushing buttons and doing, these manual things. It's not fun anymore. And I think this is the direction we're going. So automation causes a lot of problems also in terms of who is doing what. So if we are not careful, we're not creating machines that leverage us, but we are creating machines that efficiently replace us in areas where it is economically feasible. And that's the problem.